All right, here is part 3 of 4 of this series of plotting the other trig functions. Let's try to plot secant, which, if you'll remember, is the same as 1 over the cosine of x. So, since this is just 1 over the cosine of x repeats every 2 pi, so this will repeat every 2 pi. So if I can plot secant of x from 0 to 2 pi, then I'll know what the graph of secant looks like everywhere. It only depends on cosine, so let's just remember the graph of cosine. So cosine has a period of 2 pi. It starts up here at 0, 1. Cosine of pi over 2 is 0. Cosine of pi is negative 1. Cosine of 3 pi over 2 is 0 again. Cosine of 2 pi back up to 1. That's a good enough graph for my purposes. So let's ask ourselves, just by looking at that graph, where is it positive, where is it negative? Let's see, so it's positive there, negative, negative, back to positive. And remember, secant, oh well, I don't need to remind you that right here. Secant is 1 over cosine. So between 0 and pi over 2, secant will be 1 over a positive number. Well, that's positive, from 0 to pi over 2. From pi over 2 to pi, secant will be 1 over a negative number. So it will be negative. From pi to 3 pi over 2, negative. 3 pi over 2 to 2 pi, back to positive again. Secant of x is equal to 1. Let's find all the x-intercepts. So that's when secant is equal to 0. Well, secant is 1 over cosine. The only way a fraction is 0 is if the numerator is 0. Well, the only way that happens is if 1 equals 0. But that never happens. There are no solutions to this equation. What that tells you is there are no x-intercepts. All right. Secant is equal to 1 over cosine of x has a vertical asymptote when the denominator is 0. So that happens when the cosine of x is equal to 0. But I have the graph of the cosine of x just a little bit above. Of course, you should at some point just remember when is cosine 0. Looks like cosine is 0 there and there. At pi over 2 and 3 pi over 2. All right, so encoding that, it looks like secant will have a vertical asymptote at pi over 2. Let's make it thin. And a vertical asymptote at 3 pi over 2. Well, that's nice. So the last thing that I think I'll want to check is the things that will look like extreme values of cosine. So maybe I'll go off to the side and write some stuff to motivate. Let's see. The greatest that cosine x can be is 1. That is, cosine of x is always less than or equal to 1. Well, that should mean 1 over cosine of x is greater than or equal to 1. Of course, there's an issue there, provided it's positive. Right, if cosine of x is negative, and negative numbers are definitely not greater than or equal to 1. But that tells us that there should be like some sort of maximum valuiness when secant of x is equal to 1. So let's look at that. Minimum metus. Yeah. So when is secant, which is 1 over cosine of x, equal to 1? Well, let's do that. So I need to solve 1 over cosine x equals 1. To figure that out, maybe I'll just solve for cosine. So I guess that just means clear the denominator, multiply cosine to the other side. We get 1 equal to cosine of x. I want to know when is 1 equal to cosine of x. Well, I have the graph of cosine. There's a place where cosine is equal to 1. There's a place where cosine is equal to 1. So that tells me something about secant. So secant of x equals 1 when x equal to 0 and x equal to 2 pi. So that gives me 2 points on the graph. Should be go through the point 0, comma 1, and it should go through the point 2 pi, comma 1. How about negative? When is cosine of x equal to negative 1? Well, same thing. 1 over cosine x equals negative 1. Solve for that, you will get 1 equals negative cosine of x. So it looks like cosine x is negative 1. Going back up, looking at the graph of cosine to solve that equation, it looks like that's the only solution, at least between 0 and 2 pi. So that tells me that this point at pi comma negative 1 should be on the graph. Now, let's just sketch a graph that goes through those points, has the right positivity and negativity, and has the right intercepts. So, let's see, it looks like it's positive at x equal to 0, because it's equal to 1 when x is equal to 0. It needs to make it to this vertical asymptote, so it will just increase to that. Same thing, pi negative 1 is, so this y value is negative. Excuse me. This y value is negative, so it has to be negative all the way between these two vertical asymptotes, because it has no other place to change from positive to negative or negative to positive. Nice. And now, well, it's just going to repeat, isn't it? Just repeat that same pattern over every interval of length 2 pi. So let's do it. So I see that there will be a vertical asymptote right here because of this vertical asymptote. Well, you know, let's color code those vertical asymptotes then. Then there will be, shift this vertical asymptote right by 2 pi, you get this vertical asymptote. Take this point, shift it right by 2 pi, you get that point, so I already have that point. Take this point, shift it right by 2 pi, you'll get that point. Take that point, shift it right by 2 pi, you'll get there. And it's going to repeat in the same way the other direction. Sorry, that's supposed to be at pi over 2, but it looks like I missed a little bit. And then it'll repeat forevermore that way. So let's see what we can read off of this. Let's compute the, we didn't do domain and range for the previous ones. I should go back and do those. What is the domain? Maybe it's better to ask what numbers aren't in the domain. So it looks like pi over 2 isn't in the domain, 3 pi over 2 isn't in the domain, 5 pi over 2 isn't in the domain, 6 pi over 2 is, 7 pi over 2 isn't. So it looks like it's everything except for an odd multiple of pi over 2. So the domain is all x values except numbers of the form two k plus 1 times pi over 2. So I said an odd number times pi over 2. How about range? What is the range? Well, let's see. How do you determine range? You see, like, what y values do you see on the graph of the function? So these y values I definitely see, right? Keep on going, keep on going. It has a y value at negative 1. No y values between negative 1 and 1. And then all the y values bigger than 1. So it looks like the range is negative infinity to negative 1 bracket union 1 to infinity. And you know what? I know that it would have belonged in the previous ones, but let's go through and compute domains and ranges of these guys. So So the domain of cotangent x, let's see, it undefined at 0, undefined at pi, undefined at 2 pi, undefined at 3 pi, undefined at 4 pi. Looks like multiples of pi. All numbers but multiples of pi. Let's compute the range. What y values do you see? Well, these y values I definitely see. It looks like all of them. I see every y value. In fact, I see every y value infinitely many times. Range equals negative infinity to infinity, or if you prefer, all of our, everything is in the range. Tangent. The domain, well, what isn't in the domain? Pi over 2 isn't in the domain. 3 pi over 2 isn't in the domain. 5 pi over 2 isn't in the domain. Every odd multiple of pi over 2 is not in the domain. So all numbers other than those of the form odd number times pi over 2. What's the range? Well, what y values do you see on this graph? Well, you see every y value on the graph, infinitely many times. So the range contains all numbers. Neat. Cool. So that completes the information about the graph of secant, and then some.